All right, let's come back. Now, then we want to discuss about another important theorem in for the moment of inertia. Now, this theorem is called perpendicular theorem, perpendicular axis theorem, and this theorem applies only to a thin lamina. A thin lamina means a lamina, a piece of matter in 2 dimensions. It does not have a thickness. The thickness is so small that you can actually neglect it. So it means a flat object, okay, a flat object without a thickness, okay. And the so-called perpendicular axis theorem applies only to this to the flat object, but not to a 3-dimensional object. Is that okay? Now, suppose we orient the axis in such a way that the x-axis and the y-axis is in the same plane. They are in the same plane as the object. Okay, so x-y axis, they lie on the lamina itself, and the z-axis is perpendicular to the lamina. Okay, so we have 3 axes, 3 mutually perpendicular axes. 2 of the axes lies on the lamina, and the z-axis perpendicular to the lamina. Now we want to find the moment inertia about the z-axis, the perpendicular axis. So the summation I mi ri per square, that is the usual form. But what is mi ri per square? What is ri per square? Ri per square is a distance of the mass mi from the z-axis. So there's this line, right? There's this line. Now, but we notice that since the object lies on the xy plane, the distance of the point mi from the z-axis can be expressed in terms of its x coordinate and y coordinates. Now you see ri per square, because this is a right angle triangle, ri per square can be expressed in terms of xi and yi as xi squared plus yi squared. This is a simple application of Pythagoras theorem. Xi squared plus yi squared, now this distance is xi squared, right? And this distance, which is this, is yi squared. So xi squared plus yi squared is ri per square. So I replace ri per square with xi squared plus yi squared, and we separate the 2 terms. The first term is summation mi xi squared. The second term is summation mi yi squared. Now, what is xi? Xi is this distance. Okay, you see the coordinate, the x coordinate of the mass. But the x coordinate of the mass is distant from the y-axis. Is that right? Now, this distance is the distance of the mass from the y-axis. Is that right? So that means this summation is a summation of mi multiplied by the distance from the y-axis square. And that is the moment of inertia about the y-axis. Is that right? Now, how about the second term? The second term is summation mi yi squared. Yi is this distance, the y coordinate of the point mass. But yi is the distance from the x-axis, of the mass from the x-axis. So that means this summation is summation of the mass multiplied by its distance from the x-axis square. And that is the moment of inertia about the x-axis. So I now obtain a very simple and elegant formula. The moment of inertia about the perpendicular axis, z-axis, is equal to the sum of the moment of inertia about the 2 parallel axes, 2 axes that are lies on the plane of the lamina, ix plus iy. So it's very simple. So this is so we have a diagram like this. Now the object can be rotated about the x-axis, which lies on the plane, or also rotate about the y-axis, which also lies on the plane. but in the perpendicular direction. But you can also rotate about an axis that is perpendicular to the plane, right? And the three moment of inertia, they are related this way. The perpendicular axis moment of inertia is equal to the sum of the two moment inertia about on the plane, about an axis which lies on the plane. Okay, so that is the idea. Now, suppose you are given this configuration. Suppose we have a lot of point mass. We don't even have to specify how many they are. There may be many of them. And these point mass are evenly distributed along the circumference of a circle, which has a radius r. And the distribution is symmetrical with respect to the x and the y axis. Now, all the mass now, they lie on the xy plane in a circle. And the circle lies on the xy plane, and the distribution is symmetrical about the y-axis and also about the x-axis. But we don't know how they actually distribute. We only know that they are in xy plane and they have symmetry property about x and y-axis, and the mass are evenly distributed. Okay, and they are point masses. Okay. Now, so how do we use the perpendicular axis theorem to allow us to find out the moment of inertia about x and y axis? That is an interesting question. Now, we first find the moment inertia about the z axis, which is in this diagram is pointing out of the page. Can you see this diagram? X and y are on the plane together with the mass distribution, and z axis is pointing out of the plane. So z axis is a perpendicular axis. Okay. And so I form a sum of summation mi/ri per square. Now, but this, you see, because all the masses lie on the circle and they are at equal distance from the z-axis. They are the equal distance of r from the z-axis, which is just the radius of the circle, of course. And so the summation becomes mi capital R square, right? The r square can be taken out, and the summation m is just the total mass of the system. So I write as big M. Big M is the total mass of all the points, okay? So now I find the IEZ, right? But by symmetry, because the mass are symmetrically distributed about the circle, Ix and Iy, they're just the same. If you rotate the whole object about x-axis, that is just have the same moment inertia as I rotate about the y-axis. They're just the same because the distribution are symmetrical. So that means by the perpendicular axis theorem, IZ is equal to Ix plus Iy. But with Ix and Iy the same, both Ix and Iy are equal to 1/2 of Iz. And so Ix and Iy is equal to half mr squared. Can you see that? Now, although I don't know how the mass are actually distributed, right? I even don't know how many of them are there. And if you want to calculate the moment inertia about the x-axis, that would be a nightmare, because you don't know this distance. The distance is very complicated. You have to measure you have to calculate the individual perpendicular distance of the point mass from the x-axis and sum them up all together. And that is a difficult task. But now with the perpendicular axis theorem, you don't bother with that. Okay, because you know IEZ, and by symmetry, you know Ix is equal to Iy, and so you can solve for Ix and Iy very easily. Okay, so you see how powerful this theorem is. Now, why can I apply this theorem? Because this is essentially this is not a laminar, but since all the mass are on the same plane, okay, you can apply the perpendicular axis theorem. Okay, the perpendicular theorem applies to a two-dimensional object. It need not be a uniform laminar. The laminar may not be uniform. You can have point mass distribution as well, as long as all the mass distribute on the plane on the same plane, you can apply the perpendicular axis theorem. Okay. Now let us extend a little bit. We consider a disk, a uniform disk. For simplicity, we imagine that this has negligible thickness. Okay. And we want to find the moment inertia about the z-axis. The z-axis is the symmetry axis of the disk, and it's pointing out of the page. It passes through the center and pointing off the page. Okay, and we will find that by integration. Now we have this formula before, right? R squared dm. But how do we chop this? In doing integration, we have to chop the large object into many, many small pieces. And in doing the integration, we effectively form a sum of them. But in this case, how do we chop the object? Now the answer is we chop it into many rings. Okay. For example, here is one of the rings. The ring has a radius r. This is a small r, the radius of the ring, which is distinguished from the capital R, which is the radius of the whole disk. So now we have a ring of radius small r. And the thickness of the ring is dr. So the ring actually extends from r to r plus dr. Okay, it's a very thin ring. Okay, now for each of the masses inside this ring, you can see this ring actually consists of lot of mass, lot of point mass. But since the r is very small, each of these mass in the ring has equal distance r from the axis. So that's why when we do integration of r squared dm, when we divide it into rings, the r is well defined, because all the point masses inside each of the ring has an equal distance r from the axis. And so r in this case is well defined. That's why we chop it this way. Okay. But how about dm? How can we find the mass of the ring? Well, the mass of the ring is proportional to the area. And since the disk is uniform, we can find the density of the disk as the mass per unit area. And that is the total mass divided by the area, which is m pi r squared. The density, that is density. But how do we find the area of the ring? Well, the area of the ring is given by its circumference, the circumference of the ring, which is 2 pi r, multiplied by the thickness. There's a little bit of thickness, so you neglect the difference between the inner and outer radius, outer circumference. So you simply multiply the circumference with the thickness, you got the area. Okay, so 2 pi r dr is the area. And when the area multiplied by the density, you got the mass of the ring. Okay, so we put it back here to do the integration. We take all the constant r, and we are left with an integration of r cubed. So of course, the integration starts from the axis, which is r equals 0, up to the rim of the disk, which is capital R. So this is the integration range. I integrate small r cubed, and that become r4 to the divide by 4. When I evaluate an upper limit, I got 1/4 of r to the power 4. And after canceling 2 of the r here, and also the 2 cancel with the 4, and that gives me 1/2. So I got 1/2 mr squared. So that is the result. Now, some of you may not be happy to think about the area of the ring as 2 pi r, the circumference multiplied by thickness. But actually, you have a very simple proof of that using more rigorous calculus. Now, everybody knows the area of a circle. This is the area. This is the radius. The area of the circle is pi r squared. Is that right? What would happen if I have a small change in r? If I increase the r to r plus dr, where dr is a small change in thickness, what will be the corresponding change in the area? Well, the answer is easy. We simply do a differentiation. We differentiate the A. The right-hand side, we differentiate the R squared. But differentiating R squared gives me 2R dr. Is that right? So that means we have 2 pi R dr, which is exactly this. So you see why we get the area? The area of the ring. The area of the ring is this part. Okay. So that's why we multiply this with the area and to get the M. Okay. And so if you have a disc rotating about the axis, the moment inertia is half mr squared. Now we can also find the moment inertia about x and the y axis that lies on the plane by the perpendicular theorem. In this case, we find because of symmetry again, Ix and Iy are equal. Okay, and by perpendicular theorem, Iz is equal to Ix plus Iy. So that means again, Ix and Iy are both equal to half of Iz, and that is half of half mr squared. And so eventually I got 1/4 of mr squared. Okay, so that's an answer. Now remember, when we calculate the moment of inertia of the body, we will always get the formula of this form. The mass is also, or the mass of the whole body is always involved, and that is a typical length scale. For example, if you consider a rod, L must be the length of the rod. If you consider, for example, a radius of a circle, then this L will become R, that is the radius of the circle, and so on and so forth. If you consider other figures, there will be other parameters, but the parameters is a length, has a dimension of length square, so that you have a typical dimension of the length of that object square, and multiplied by the total mass of that object, and you have a numerical dimensionless number in front. This number you don't can really guess from the shape of the object. You have to do an integration, most of the time. So in doing all the integration, you actually amounts to only finding this the dimensionless number, and the rest of the form of the object is mr squared. You can guess it. Okay. Now you should always notice that the moment inertia found should be of this form, should be of the dimension of mass multiplied by length square, a certain length square. If you find that the moment inertia is your answer is not in this form, you might have done some calculation wrong, and you better check it. Okay, so that is the idea. Now we also have another example. You have a semicircle like this. That is a lamina, okay, without thickness. Okay, it lies on the XY plane. Now this problem we actually have encountered before, right? And in the last chapter, when we talk about the center of mass, we find that the center of mass y above the x-axis, above the base of the semicircle, is 4r over p pi. This number we found before in the last chapter, in the example of the last chapter, right? Now, what we are going to find now is if you have a semicircular disc of mass m and radius r, the first part is to find the moment inertia about the z-axis. The z-axis is the center of the semicircle, and it's perpendicular to the plane of the semicircle. Okay, so what is the moment inertia about that axis? And then you are required to find the moment inertia about an axis that passes through the center of mass and perpendicular to the plane of the semicircle. Okay, so how would you do that? What is the answer for the first part first? For the first part. Now, look at the definition. We now define the mass m, not the mass of the full circle, but the mass of a semicircle. What is the moment of inertia of a full disk about an axis passes through its center? You know the answer, right? The answer before is half m/r squared. Is that right? What will happen if we divide it into half? If we consider only the upper part but not the lower part, we now have a semicircle. So how would this change? Now, because the moment inertia is a summation, and if that is a summation, that means you can separate the summation into two equal parts with equal contribution, right? So you can actually spread it. For this part, for the shaded part, and for the unshaded part, you also have another term like this, right? So each time corresponds to the contribution of one of the semicircle, right? But now you notice that in our definition, the mass m is not defined as the mass of the full circle, but the mass m is defined as the mass of the semicircle, which corresponds to m/2 here in this expression, right? So that means in this situation, the moment inertia about this axis is simply m/r squared, because we call the m the mass of the semicircle. Okay. Do you get this? Now the second question is about the moment inertia about an axis that's passed through a cm, right? And in that case, we have to apply the so-called parallel axis theorem, right? To find IC, we need to apply the parallel axis theorem, right? IA is this axis. A is just the axis that passes through the center of the semicircle. And C is just the axis that passes through the center of mass. So they're just related this way. Y is the distance between them, which is found in the last chapter, right? So we just apply this formula. If IA is half m/r squared, and Y is this, then IC is here. Then this minus this will be IC, right? I put the n/r squared r anyway. This is 1/2 plus 16 divided by 9 pi square. Oh, sorry, this is a minus sign. So this is the answer, okay? Okay, so that's how we find IC, okay? Now, if you want to learn more about moment inertia, you can take a look at this e-learning module by Professor Kenneth Yang. Now we come to an important part of our discussion, that is Newton's second law for rotation. Now we emphasize the similarity between the formulation of the linear motion and this angular motion and the rotational motion. For linear motion, we have the coordinate x. For angular motion, we have the angle theta as the angular position. For linear motion, we have linear velocity. For rotation, we have angular velocity. The linear acceleration goes to the angular acceleration. The mass m goes to the moment of inertia. right? So we have a one counterpart between the two formulation. Okay. But in one-dimensional motion, we have the force, right? So the force corresponding to what in the angular formulation? Now, eventually, we'll find that the force in one-dimensional motion, when it translates into the rotational counterpart, it corresponds to the torque or the moment of force. Now, the word moment of force is what you learn in high school. 力矩啊，呢住 When you multiply the force by the moment arm is distance of the application of the force from the pivot of rotation, right? You get the moment of the force, right? The moment of the force is formally called torque. This word, torque, T-O-R-Q-U-E. We introduce later. Okay. Now, how do we derive this? How do we derive torque? What is the expression for torque? Now, let us have an energy consideration. The energy consideration is like this. We know that the work done by a force in moving the object by a distance delta x is F delta x. That is the work done by the force in when the object moves a little bit of distance, right? Is that right? How about rotation? If I now apply the torque to the object in rotation, and I find that when the object moves a small angular displacement of delta theta, the corresponding work done is equal to torque multiplied by delta theta. So I draw a similarity as analogy through with the force. If the force multiplied by delta x gives the work, similarly, I propose the torque multiplied by the angle, by the displacement in the angular case, should also give the work. So that is how I want to define the torque. Okay, I define it in terms of the energy consideration. So let's see what this will bring us. Okay, what expression of tau this definition will bring us. Now we consider an object in circular motion again for simplicity. The force applied on that object may be in a general direction, but we resolve the force into two components. The first component is the perpendicular component. What I mean by perpendicular is that it's perpendicular to the radius r. So the perpendicular component is actually the parallel it's actually the tangential component in this case. And we also have a radial component. The radial component is parallel to the radius. So I denote it as F parallel. Now, when the body moves a small distance forward, the parallel component of the force does not work because it's perpendicular to the displacement. It is the perpendicular component of the force that does work. So the work done is the perpendicular component of the force multiplied by the small distance. The small distance is the arc length here. When the object rotates a little bit, it moves through a small distance delta s, which is the arc of this of this circle. Okay. Now delta s, the arc length, is equal to the radius multiplied by the angle that is turned through. So it's equal to r multiplied by delta theta. So we change delta s into r delta theta. Now we grouped the two terms, the two parameters together. F per multiplied by r multiplied by delta theta give me the w, the delta w. And so I identify this as a torque, right? Because my definition, torque multiplied by delta theta give me the work done. So I can identify this combination, the perpendicular component of the force multiplied by the distance from the point of rotation as a torque. And you can see from this definition, that the unit of torque is Newton meter because the unit of force is Newton and the unit of distance is meter. So the unit of torque is Newton meter. Now the torque has the same dimension as energy and work. Why? Because when you see this formula, delta theta is the angle. And if the angle is given radian, it does not carry a dimension. The angle does not carry any dimension. So that means the dimension of torque must be equal to the dimension of work, which is Newton meter. And that's joule, okay? That's joule. Okay, so that's why torque has the same dimension as energy or work. Now there are actually two views of torque. What we define in our previous slide is that we take the perpendicular component of the force and then we multiply by the distance from the point through which the object is rotated. So we have F per multiplied by R. And if you like, you can express it in terms of this angle. Now this angle is the angle that force makes with the radial direction. This is the radial, the radius, the radial direction. This is the angle phi, the force makes with the radial direction. So in terms of this phi, I can write the F per as F sine phi. Is that right? So the torque expression becomes FR sine phi. But I can also look at this from another point of view. Instead of taking the component, the perpendicular component of force, now I consider the line of application of this force. We extend it a little bit backward. So this is a line of application of the force. So this is a dotted line, which is just an extension of the line of the force backward. And we define this distance, R per, as the perpendicular distance between the line of action of the force with the pivot point, okay, with the pivot. So R per is a line distance between the line of action of the force from the pivot. Okay. Now you can see in this diagram, I can define the torque as F multiplied by R per. Instead of F per multiplied by R, I now define it as F multiplied by the perpendicular distance. Now you can see R per is just R sine phi. So I can write R per in this triangle. I can write R per R sine phi, and that gives me again F R sine phi. Now this angle is the same as this angle. They are the opposite angle, right? So it just gives me back F R sine phi, which is the same as this. So it just depends on what you like. You can choose either expression you find more convenient. And in your high school, you may prefer this point of view. You multiply the force by the perpendicular distance from the axis. Okay. Now for linear motion, we have F equal to ma, right? That is Newton's second law. And A is can be written as dv dt, is that right? That is the rate of change of the velocity, is the acceleration. And if we put the mass m into the derivative, inside the derivative, we got dp dt, where p is the momentum given by mv, is that right? Now for rotational motion, we actually expect a similar thing to happen. The counterpart of the force is the torque, right? The counterpart of the mass is the moment inertia. The counterpart of the acceleration is the angular acceleration. It would be nice if the three quantities are related in the same way as the Newton's second law for the linear case, right? If I can translate all this quantity into their rotational counterparts, and they form the same, almost the same expression as the linear case, that would be very nice. So I expect a formula of torque equal to I alpha. And since alpha is the omega dt, the time derivative of the angular velocity, if I can put the I into the derivative, and I define a quantity called L, then I will have the torque equal to dl dt. Now you see this form of the Newton's law for rotation is almost identical to, it's very similar to F equal to dp dt. So if P is a linear momentum, then I could define L, which is equal to I omega, as the so-called angular momentum. So the torque is equal to the rate of change of angular momentum, just like the force is the rate of change of the linear momentum. Now, but all these things are just my guess at this moment. I haven't proved that before. But in the next slide, I will prove it. I will try to prove it. All this formula. Okay, and I find that all this formula is in fact true, in fact hold for rotation. And we also will define the angular momentum L formally. Now, how do we define the angular momentum? We define the angular momentum like this, just like the torque. Now, you see how do I define the torque? The torque is the perpendicular component of the force multiplied by the distance from the axis of rotation, right? Now I take the perpendicular component of the linear momentum. If the linear momentum is in this direction, I resolve a perpendicular component I call P per. And then I multiply the distance of the particle from the origin, okay, R. And so that is defined as the angular momentum of a single particle about the origin. Now this definition is for a single particle only. Now you see angular momentum is unlike linear momentum. You have to define the angular momentum with respect to a particular origin. The linear momentum is somehow independent of origin. You just multiply m with v. But now the angular momentum has to be referred to a particular origin. Okay, you have to specify that origin. Otherwise, this R will be meaningless. Okay. Now the P per is a perpendicular component of the linear momentum. So if you write this P per as linear momentum mv, and the perpendicular component just give you a factor of sine phi. And so the angular momentum for a single particle is expressed as mvr sine phi. Okay. Now consider a rotating rigid body. Now a different particle are rotating with the same angular speed but not the same linear speed. Okay. The angular velocity is common about the axis of rotation, which is now drawn at the x-z axis in this diagram. And so the angular momentum of a single particle mi here is mi vi ri per. Now because my velocity, my linear velocity is now perpendicular to the radius in a rotation. In a rotation, the linear velocity of the particle is always, because it's in circular motion, right? So it's always perpendicular to the radius. So that means this sine phi is equal to 1. The momentum is actually in the direction perpendicular to the radius. So we don't need this sine phi. This sine phi is just 1, okay? So we have mvr as the linear momentum. And the r is a perpendicular distance, so we have ri per. We just write it as ri per itself, just ri. And we form a sum of all the particle, all the linear momentum of the particle. And we find the total angular momentum of the system. Okay? The total angular momentum is just a sum of the angular momentum of the individual particles. Okay? Now vi can be written as what? As ri per omega, is that right? That is a circular motion formula. Circular motion formula is so useful. Everywhere I'm using a circular motion. V is r omega. Now I take the factor omega out because it's common to all the particle in the object. They all share the common angular velocity, so I can take it out. And you can see now what is inside the bracket. What inside the summation is summation mi per square. But that is exactly the moment of inertia. So now I have the moment of inertia multiplied by omega equal to the angular momentum. And that is exactly what we expect, right? We expect something like this, right? I omega is L. L is angular momentum. So we succeeded in defining L to be I omega. If we define the angular momentum like this for a single particle, then eventually for a system of particles, we got the angular momentum as the moment of inertia multiplied by the angular velocity of the object. Okay. Then we should prove the Newton's second law for rotation. We use the energy approach again. Now, if I apply a torque on a rotating object, and after I apply a torque for a while, the object changes its rotational speed. It changes angular velocity. So I can apply the work energy theorem. The energy that I deliver by my torque to the system must be equal to the change in kinetic energy, right? That is the work energy theorem. I input some energy to it, now by a torque, but not by a force. But that is a similar idea. That energy must go through the change in kinetic energy. Okay, so I now write down this formula: dW is equal to dk. But as I say, dW is equal to torque multiplied by the angle. When the object moves a little bit angle d theta, the work done by the torque is torque d theta. The kinetic energy of the particle of the object, because now it is in rotation about an axis, k is equal to half I omega squared. So we differentiate the k, meaning that we differentiate half I omega squared. So the differential x on omega squared, and of course that gives me 2 omega d omega. The 2 cancel with the 1/2. So I got I omega d omega here. Now I would like to divide the equation by dt on both sides. So the left-hand side of the equation now becomes tau torque d theta dt. Tau d theta dt. That is the left-hand side. And for the right-hand side, I have I omega multiplied by d omega dt. Is that right? Now, but I know d theta dt is actually the angular velocity omega. That is the definition. The change in the rate of change of the angle is just the angular velocity. And the change in the rate of change of the angular velocity is just the angular acceleration. So the omega dt is alpha. I can see the omega, there's one of the omega cancel on both sides. Okay, the omega on the right-hand side cancel with d theta dt. So eventually I'm left with tau torque equal to I alpha, which is again exactly what I expected. Okay, the torque is equal to the moment of inertia multiplied by the angular acceleration. That is exactly the Newton's second law for rotation. So we write the angular acceleration of body is proportional to the net torque acting on it, and is inversely proportional to the moment inertia. Now I just copied this sentence from what? From linear motion. In linear motion, Newton's second law, you say the acceleration on a body is proportional to the net force acting on it, and is inversely proportional to the mass of the body, right? Now for angular thing, you have the angular acceleration instead of linear acceleration. Now it's proportional to the net torque, not the net force. But it's inversely proportional to the moment of inertia, but not the mass. So everything carry over to the rotational counterpart. So that is nice for us. Now, there's a long lecture, so let's stop here. If you have